The key is we must not think all this stuff is foolish. We must think out of the box. And many of the techniques needed for interstellar space travel haven't even been thought of yet. And many of the, from the list I was trying to give you there, many of the problems haven't been given realistic consideration. Realize everything is moving too. So it's not like just pointing your rocket at one place and getting there. You've got a lot of things to do. Okay, some light speed technologies. All right, I'm going to cover five technologies here. Okay, be aware that each of these technologies have a higher efficiency or specific impulse than conventional chemical rockets. Okay, so they're better. What does that mean? Well, let's first consider our five technologies. We have solar sails, okay, which I'll go into. Okay, and we have electric propulsion sails. Okay, this is different. Solar sails are powered by light, photons. Electric sails are powered by ions. The sun sends out not only photons, but also ion stream. And so the electric sail we could use, it would be actually ions from the star. Okay, the second one that we're going to be talking about is ion electric propulsion. This one is actually quite exciting because we're actually using it today. Okay, the Dawn spacecraft was powered by ion rockets. Okay, and we'll talk about them. The next one is fission propulsion. And fission propulsion got its start back in the 50s, and we dropped it because of fear of nuclear fallout. Of course, fusion propulsion. And NASA thinks that we will have full-scale fusion propulsion within 25 years. And Lockheed Martin has come up with a technique, which I'll mention, which says it might be a lot closer than that. And finally, our last sublight rocket uses antimatter as a propulsion unit. This can reach 67% the speed of light. Okay. So, solar sails. And I put down driving the windjammers of interstellar space travel. Okay, as I mentioned before, there are two. If you look at a comet, this tail is actually the result of the solar pressure, both photons and ions. That's why it's actually got two tails. Okay, and that is what you see here. The solar sail is powered by photons. And with these solar sails, you can obtain 0.02 of a pound of thrust. But and that's about as much as a packet of sweetener exerts on your hand when you put it on the hand. That's how much thrust they generate. However, in space where there's no gravity, and that thrust lasts for a long time, and it's continuous. Unlike our current rockets, which takes so long, so you got a lot of bing at the bang, at the beginning, but then you've got to coast, and then you've got to use acceleration from the planets, and you've got to go all through high. With these type of things, you can launch them and forget them. Okay, the solar sail, so 0.02 of a pound of thrust. Although minuscule, it's continuous and unlimited. The key with solar sails is the bigger and lighter, the better. Okay? Most solar sails have a thickness of 4% the thickness of a human hair. Okay? And there was a Halley's Comet proposed solar sail that would have had fins, a sail, 4 miles long. Sounds great, huh? I read about the one that they said proposed for interstellar space travel that would have a solar sail the size of Texas. Solar sails eventually can reach speeds greater than is obtained through chemical rockets. In fact, they can achieve speeds of 1/10 the speed of light. Okay? And this speed would be achievable if you have attached laser to your spacecraft or a magnetic beam transmitter. Okay? So if you have an attached laser on your spacecraft, you can achieve a speed of 1/10 the speed of light. Without a laser assist, you can achieve a speed of 56 miles per second, or 12 times faster than the space station orbits. Okay? Be aware, solar sails are only good about out to the unassisted solar sails, about to the orbit of Jupiter. Beyond that, you need assistance. It would take about 30 days to 70 days to go to Mars using a solar sail. Okay, which is really pretty good when you consider it took 8 months for Voyager to get to Mars. So the thing we want to do is we want to make sure we go interstellar, we're going fast. We want to get there quick. We don't want to be exposed to radiation and all those other things for too long. The Planetary Society is currently actually testing a solar sail. They launched a solar sail device back in 2015. It will be used to power something called the CubeSat, okay, which is right over here. CubeSat is about as big as a loaf of bread, and it weighs about 9 pounds, and it's very cheap. As a result, you can expect groups like this, and schools, and universities especially, to have their own spacecrafts. Okay, they'll be cheap. The solar sail that we're talking about here was actually funded by my group to the tune of $4.5 million. Back in 2015, they launched it aboard an Air Force Atlas rocket, and we just tested, can we deploy it? It wasn't put high enough to actually go anywhere. However, this year in June, we're going to launch aboard a Falcon X, SpaceX Falcon rocket, and we're going to actually test the ability of solar sails to power our craft. Okay, this will be the first working solar sail. There was supposed to be others, but for one reason or another, those programs got canceled. Okay. Now, the next technology, which is very interesting because this is actually being used, is ion electric propulsion. An ion, for those of you who don't know, basically an atom or molecule where the number of negative electrons does not match the number of positive charges in its nucleus. As a result, it has a net positive or negative charge. That's an ion. All right. The plasma, which is produced from the fuel provided, okay, through various techniques. Here we have a cathode ray electron gun type approach, okay, which is the currently used approach where you inject a gas, you ionize it through a technique, whichever one, okay, you have a discharge chamber. The ions are then accelerated through a grid, an anode. It's like a big old-fashioned vacuum tube, to be honest with you. Okay, and then the ions are accelerated out the back end as thrust. There's magnets around the chamber, which allows you to take the orbital motion of the ions and direct it into a thrust stream. Okay, and then one over here, we've got an ion gun. Once they get out, we have to neutralize those ions so we maintain the thrust. Okay, NASA Now, before I get to NASA, despite the low amount, thrust here. The amount of thrust that's available on an ion rocket is 0.5 newtons, which is 0.1 pounds. Okay, and that's a very small thrust. It's equivalent to a few coins dropped in the palm of your hand. Okay, chemical rockets, on the other hand, produce thousands of newtons of force, but for a very short time. They get you up into orbit and can't use them much anymore. Okay, despite the low thrust, the ions can accelerate the spacecraft to 112,000 miles per hour. Not bad. Not interstellar space travel good, but not bad. Okay, chemical rockets have demonstrated a 35% efficiency, whereas ion rockets have a 90% efficiency of fuel. NASA currently uses xenon gas as the fuel source, okay, the fuel. And it said 35% versus 90%. And ion rockets use between 10 to 100 times less fuel than conventional rockets. So this is the way to go, okay, as far as technology is concerned. At least to get to the solar system planets. Okay, I think so far of the two technologies, the one that might be used, practical to use, is the solar sail. Remember, you need to just simply have a laser shined on the sail. But that laser, another interesting thing, will have to operate for years at a gigawatt level. Okay, a lot of time, gigawatt level, what does that say? Lots of electricity, got to come from someplace. Okay, the Dawn spacecraft, okay, was launched in 2007, okay, and it carried 1,000 pounds of xenon gas, okay, reached a speed of 25,000 miles per hour, and cost all of $446 million. And it was sent to visit the dwarf planets of Vesta and Sirius. And did a very excellent job. For those of you who've seen pictures, it's unbelievable what's there. Those asteroids are fascinating. Okay. Here is the next generation ion electric engine. It's called the Vasimir Variable Specific Impulse Magnetoplasma Rocket. Okay? This does not use a grid, so it's not susceptible to grid decay, which is one of the problems with current NASA ion rockets. Okay? And the technique for ionization is considerably different. Okay, a gas, which could be xenon, argon, or hydrogen, so not just xenon, is injected into a chamber that's surrounded by magnets, which accelerate and convert the gas into a plasma. The first using RF couplers. The first coupler, called the hexalon coupler, raises the temperature to 58,000 degrees Kelvin. Okay? 5,800 degrees Kelvin, excuse me. And that's considered a cold plasma. Okay, I apologize there. The next coupler, that does a better thing. It raises the temperature of the cold plasma to a hot plasma at the temperature of 10 million degrees Kelvin. A little bit warm. As warm as the center of the sun. And then a magnetic nozzle takes the orbital motion of the plasma and turns it into a stream that's used for propulsion. Okay? Not having to worry about grid decay makes this engine far more reliable than the conventional ion engine, okay, able to generate over 100 times more thrust than the conventional engine. Okay, and I mentioned that. Okay, so this is the one that's going to replace the existing system. This is currently being built by a company called Ad Astra in Texas that's headed up by a former astronaut. Now, having said that, be aware that there are issues now that they've discovered with this engine. So you might look it up on the internet and find out what those issues are. Okay, again, another big issue, a lot of electricity. You notice those temperatures aren't coming from nothing. All right, next. Okay, the next type of propulsion that we consider is fission. Okay, nuclear fission is actually quite old. The first nuclear fission rocket was the nuclear pulse propulsion. Okay, this rocket was proposed back in the 50s, where they would explode an atomic bomb behind the rocket and use the atomic bomb to provide thrust. Okay, and several atomic bombs, and you just drop them and it'd be bang, 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 bang. Okay, really nifty, except a lot of fallout. They originally were proposing launching it from Earth, but it got canned in the 1963 partial test ban treaty. Okay, so nuclear pulse propulsion was not a very good idea launched from the Earth. But in outer space, you could do it. And there are proposals for doing that today. However, the engine most likely to be used is the nuclear thermal rocket engine. Okay, the nuclear thermal rocket engine, by comparison to traditional, is much more efficient than current rocket engines. Okay, so it has over twice the specific impulse of conventional rocket engines. And basically what you have is you've got a fuel, a lightweight fuel, hydrogen, liquid hydrogen, normally, and you pass the liquid hydrogen through a nuclear reactor, which is very hot, and the result is an expanded gas which provides propulsion. Okay, because of its scalability and compact nature, a fission reactor is an ideal power source for spacecraft propulsion. In fact, the Russians are going to try one. That's what they said. If I don't believe it, hey, you know what? You get a person like me, I don't care what country does it. I want to see us do it. Okay, but I'd like us to be the first. Okay. That's the wrong one. That's fusion. Okay. So that's nuclear fission. Okay. Next propulsion technique, which is another one that could get us to the stars, is fusion. I know I'm behind, but I had, yeah. Anyway, two fusion propulsion techniques are currently being investigated. The first, okay, is called inertial confinement fusion, and the second, magnetic confinement fusion. Okay, magnetic confinement fusion, actually I should talk about first, although, well, it really doesn't matter. With magnetic confinement fusion, you take a gas which you ionize using an RF coupler similar to what you saw earlier for the Vasimir rocket, which takes the ions, okay, turns it to gas, runs it through a magnetic field where they're compressed until the atoms fuse. Okay, fusion is actually what fusion is overcoming the Coulomb interaction between the nucleus of the atoms. Okay, the ideal fuel for fusion reactions is deuterium-tritium or lithium-6. And lithium-6 is the equivalent to the Star Trek, what's that metal that they were? Dilithium crystals, right, yes, that's it. It's the dilithium crystal. For those of you who don't know, the impulse engines on Star Trek were fusion engines, okay? And these red things are there. Now, what you see here is Dilius. Dilius was proposed in the 1970s by the British Interplanetary Society. Here, this uses inertial confinement instead of magnetic confinement. Oh, and by the way, you heated the plasma, you sent gas, cold hydrogen gas, the other direction. The plasma, the heated plasma from the fusion, heats the gas, and that causes you to have the propulsion. Okay? Here, inertial confinement, you have pellets of deuterium-tritium, which you shoot in and then use lasers to cause the fusion. Now, the rocket that was proposed for this, what you see here, is a rocket called the Dilius spacecraft. It was about the size of a Nimitz-class spacecraft. Okay, actually it contained, was proposed to contain 54,000 tons of